So, let us consider the polyphase representation of a 2-channel filter bank. Right. So, let us start with a base filter H naught of z, and we can write this as E naught of z square plus z power minus 1, that is a delay, E1 of z square. Now, this is basically a 2-phase representation for the filter H naught of z. If we assume quadrature mirror property, then H1 of z is basically H naught of minus z. So, I can write H1 of z in terms of polyphase representation as E naught of z square minus a delay with E1 of z square. Right. I am just replacing z with minus z in H naught, right, and that is a representation, polyphase representation for the filter H1. So, now I can stack the filters H naught of z, H1 of z, and combine them together as a column vector and express this in matrix form using the polyphase components. So, I have E naught of z square, then I have z power minus 1, which is a delay, E1 of z square. So, I have 1, 1, 1, minus 1. So, this is the representation, polyphase representation for the analysis bank. So, this is the analysis bank representation. And we can do this similarly for the synthesis bank. Basically, we will use the conditions for the alias cancellation. Using alias cancellation conditions, we have f naught of z is h1 of minus z and f1 of z is minus h naught of minus z. So, using this representation for the synthesis filters, so we can express them as follows: f naught of z, f1 of z stacked in this row format is basically a delay with E1 of z square, E naught of z square with 1, 1, 1, minus 1. So, this is basically the synthesis filters realized using 2-phase representation. Okay. So, we have both the analysis and the synthesis filters that can be realized using polyphase representation, and we will see this is going to be very useful for us, because when we have to do multi-rate operations and realizing these filter banks through possibly generalizations from 2-phase to M-phase, then we will find these representations very useful. And one of the things that you might have noticed is the form of representation, right? For the analysis, somehow I wrote it in this form where I stacked them in the column format, and synthesis I did this in the row format. And the hint would be the type 1 and type 2 phase representations that I would want. Type 1 polyphase for analysis and type 2 polyphase for the synthesis. That is the sort of idea why we have stacked these filters in this form. So, let us look at the signal flow graphs for this, for realizing these filters. For a polyphase realization. So, we will start with analysis bank. So, we have x of n this goes through the filter E naught of z square. Then I have a delay element this is filtered through the filter E1 of z square. Now, I take this component here add them up with this branch, I get x naught n, then I have a gain of -1 here, I add from the first polyphase component and I get x1 of n. So, basically this is sort of a two band representation. Two subbands we have, and we have signals x0 and x1 that are realized through polyphase representation. So, this is the analysis bank. Similarly, we have the synthesis bank. We have y0 n coming in. This is filtered through the filter E1 of z square. We also have a filter E0 of z square in a parallel branch, and y1 with a gain of -1 will be fed here, and then we take the component from y0, add it to this branch, and here we directly take this subband signal and add it here. So, we get, so basically two different subband signals, one is a sum, other is a difference, goes through each of the filters, and then the output of the filters are combined using a delay element to get you back your reconstructed signal x hat. This is the synthesis bank. So, all we have done is just the polyphase representation. We have not used any downsampling or upsampling, right. We have to bring in those components as well if we were to realize the entire 2 channel filter bank. This is just a polyphase representation. Okay. Now, once we have understood the basic components, we can connect all the dots. Yeah, before we wrap up with this slide, just a small detail, an arrow here has to be pointing in this direction. But before we begin the generalization, I would like you to go through a simple example of a 2 channel perfect reconstruction system. We will see an example so that we know what is happening purely in the time domain. So, suppose we have the analysis filters as follows: H naught of z is 1, absolutely no filtering is just a gain. H1 of z is a unit delay, F naught of z is a delay, F1 of z is just a unit gain. Okay. So, we can sketch this, we can sketch the schematic of the 2 channel system along with the downsamplers and upsamplers. So, we have x of n, then this goes through a downsampler because there is unit gain here, right. H naught is 1, so therefore, I am just not putting any filter here. Now, in the other branch we have a delay which is corresponding to this filter H1 of z. This goes through a downsampler. At this point we have V naught of n and V1 of n. Let us assume that we do not do any quantization, etc. So, basically we just upsample by 2 on each of the 2 branches. We get U naught of n and U1 of n, and in the synthesis stage F naught is this delay. So, therefore, I have to put a delay element here because this is a filter, and second branch this is just unity gain, nothing. So, therefore, I am just leaving this branch as is. So, now this is our x hat of n. So, let us examine if the system above, or I would say system in this example, is perfect reconstruction, is a perfect reconstruction system. Now, you may even wonder what is happening here. Basically, if I give you a signal, I am just delaying it, I am considering the even parts in one side, other is the odd parts, and then I am just expanding them and combining them using delay. So, I think intuitively this should just be a perfect reconstruction system, right. But let us just work out through an example, figure out all the interim points V naught, V1, U naught, U1, etc., and then see what is really happening. So, let us take for granted that x of n is, suppose x of n is a ramp. Maybe I just take about 8 values, 1, 2, 3, 4, 5, 6, 7, 8 dot dot dot. Okay. Now V naught of n is the downsampled signal, right. So basically we have only the odd components 1, 3, 5, 7, so on, because we are considering only the alternative samples here, alternate samples. Now V1 of n is basically you take a delay element and then you downsample, right. So basically at the first step you may have some value, then you will end up with 2, 4, 6, 8 dot dot dot, right. So basically if you introduce a delay, the reference something here which would have been some element in the past before time 0, let us say that variable is x, right. You will have x, if you delay that you have x 1, 2, 3, so on. Now if you downsample you get x 2, 4, 6, 8, clear. So this is a dummy variable indicating some value that would have been possibly before time equals 0. So this is basically time equals 0. Okay. Now we have V1 of n, maybe in the interest of, I will call this as n just to be consistent. So n equals 0, n equals minus 1, we had some x here. So therefore, and then when you downsample you get x 2, 4, 6, 8. Now u naught of n is the upsampled version of V naught of n. So therefore we have to insert zeros. So you have 1, 0, 3, 0, 5, 0, 7, these are all insertions. Then u1 of n is basically x 0, 2, 0, 4, 0 dot dot, where these are the insertion points, right. At every even time step I am just inserting these, or odd time step I am inserting these. Now you have a delay element for u naught of n, right, because u naught goes through the filter f naught of z, and therefore you get u naught of n minus 1 and u naught of n minus 1 is maybe some element in the past, I call some x, right, because there is a delay, therefore something before n equals 0 is what I am going to get. Then I am going to delay it. So I have 1, 0, 3, 0, 5, 0, 7 dot dot dot, and then I take u1 of n and I add it with u naught of n minus 1. I get some value, I call it as dummy x, then I have 1, 2, 3, 4, 5, 6, 7, I just can reconstruct my sequence. So this x is dummy. So do not worry, this is some variable x, so therefore this is x1, this is x2, and do not get confused with all that. So x is basically a dummy variable for just place holding the value at time step n equals minus 1 and before then. Okay. So we now have, we are reconstructing the sequence back but with a delay. So, note we have perfect reconstruction with a delay of 1 unit, and this is the delay. Just say n equals zero here, and that means I am shifting the original sequence by 1 unit. Okay. So, now if we were, the real question is, this is a very simple filter bank, 2 channel filter bank satisfying the perfect reconstruction property, and of course we have considered only delays as some of our filters, but in practice it may not be the case, because you may have to filter out certain components in the low pass, some other components in the high pass, and then come up with reconstruction filters. So, it is not very straightforward like the way we looked at the delay filter bank, because the filters can be quite sophisticated. So, then it would be very useful for us to think what are the conditions for perfect reconstruction property. How do we design synthesis filters such that the overall transfer function is of the form Cz power minus n naught, where C is some amplitude which is not 0 and the output comes to you with a delay of n naught units. Okay. So, the design of such synthesis filters that can give you perfect reconstruction, I think this is of great interest. So, we will stop here.